Greetings everyone, it's Reed here. Today, we have a geek video. Now, I'm going to make this as understandable as I possibly can to really help convey the message. So if you are a physics person or an electrical engineer and you're going to be like, you crazy bleep, well, I'm trying to bring this down to a lower level here. I mean, it's a simple lesson, at least in my mind, but for a lot of people, they may not have ever been exposed to this material. So we got to try. So if you're gonna be griping about the nuances of some of this, please don't bother. We can do that some other time. But today's video is on watts, amps, and voltage drop, and heat. All very important things when we are building solar systems or any electrical based system and design. A lot of things we're doing out in this area, especially when we're DIYing, analyzing, doing stuff, well, they are custom and very specific to what we're after. And a lot of times people are cutting corners that really shouldn't be cutting corners, or they're lacking a fundamental understanding of something that's very important. Today, I'm going to try to clear up some of that by laying out some basics. Let's start here with voltage. Now, voltage in the scientific sense is defined as the charge potential between 2 points. So, like the terminal posts on a battery, we've got the negative and the positive. The difference between those two, put a voltmeter on that says, like 12 volts, right? Now, in the actual equation, 1 volt equals 1 joule times 1 coulomb. And there's other methods of defining it. Now, yeah, that may not make a lot of sense. Basically, let's say we have a pile of electrons on one side, and they want to get over to the other side because there's lower potential. That potential is a voltage, basically. Yes, that is oversimplified immensely, but just think of it that way. Let's go with that. Now let's relate this to another analog. Say a plumbing system. Lots of people know plumbing, play with it. I mean, everyone's got a faucet they turn on and off. Well, think of voltage as sort of the pressure in the water pipes. That PSI reading is a voltage, so to speak, in the terms of, our electrical conductors or a water pipe. Now just go with it. I know this is a simplification, but let's just go with it. Now the next thing we're going to need to talk about here is amps and amperage. Now in the scientific sense, amperage is defined as sort of the electromagnetic force between two conductors carrying a current. Oh yeah, that makes a ton of sense, right? Think of it as the mass of electrons flowing through, and that sort of width that they have, or that their space they're taking up as they're going through the wire, and that corresponding amount is amperage. Now when I relate this to a plumbing system, I like to think of, amps, it relates to the wire, sort of the diameter of the pipe, okay? The wider the diameter of the pipe, the bigger the amperage it can handle safely. Yes, that is a huge oversimplification, like I said. Let's just go with it, okay? But think of amps as like, big bunch of electrons marching down a wire, going down there, that whole pile of them moving along, that's the amperage, okay? And then, of course, the pressure behind them, that's the voltage, okay? Now that we got the voltage and amperage down, I'm certain everyone fully understands it now, right? Good. Let's move on to the really important part, the unit of energy we're going to work in a lot, watts. Watts is a measure of the energy being consumed here, and it's a direct relation to amperage and volts. To calculate watts, you take the voltage times the amperage. Now, since I'm, not a super math genius, we'll kind of move the screen around a little bit and kind of get something a little fancy off to the side. We'll see if I can make this work, and it makes people happy at least. And it'll give some real good examples. Now let's play with a 100-watt light bulb, okay? And we're going to power it 3 different couple ways. And the wattage is going to stay the same, but we're going to vary the voltage and the amperage needed to do it. And they all result in the same energy calculation, but there's an important distinction that emerges. First, let's say we want to power this 100-watt light bulb with 100 volts. Well, a 100-watt light bulb, to get 100 watts with 100 volts, we need 1 amp, okay? Now, say we're going to do it at 1 volt, right? Well, to get a 100-watt light bulb to run with 1 volt of voltage, we need 100 amps. Okay, so what does that mean? What's that doing for us? Well, if you think about in terms of plumbing, right? Okay, if you have a tiny pipe, okay, but it's got tons of pressure behind it, and you open it up, well, it can fill something real quick, right? Well, say you got a huge, big, wide diameter pipe, okay? You open it up, but it doesn't have much pressure, it can still fill something quick because there's so much coming out at once. It's the same thing we're dealing with here. The higher voltage, higher pressure, we need a smaller pipe to do the same thing. Now let's pop over the Nec Ampacity Table and take a look at what this variance means. Now, at 100 volts, all we need is 1 amp. We look at that, go to the chart, hey, 14 gauge wire. This'll do it, no problem. In fact, you could run like 10 of them without any problem. Hey, that's pretty cool, right? Yeah, sounds great. Now let's take a look at that 1 volt option. 100 amps. Go down the chart, go down the chart. Wow, that's a bigger cable, isn't it? You know, let's take a look at an example cable that could do that. This is 2 watt, 14 gauge. This will do it. I can do like 1. We got a difference here, don't we? That's like what I'm saying on the plumbing side. Small pipe, lots of pressure. Big pipe, not much pressure. You can equal up, but what you need to work with here is very different. Okay? All right, now that we've got this watts energy thing and big pipe, small pipe worked out, let's transition to going the distance. Let's say we want to power a 1 kilowatt load 1,000 feet away. Like we got a shack we're going to set up, and we're going to put an air conditioner in there. It's hot and all that stuff. We're going to do that. Now, because we are complete masochists, we're going to run 12 volts, 1,000 feet. Can it be done? Yes. Yes, it can. And this could do it, right? You know, we're dealing with 83 amps for a kilowatt, right? Well, we got a problem here. See, as current and stuff, as the energy flows down the wire, we'll go with energy, right? A little bit is eaten up. Each little further and further it goes because wire has resistance. I don't really got room temperature superconductors to work with here, so we got to deal with this problem. And if I invent those room temperature superconductors, you'll find out I'll be a trillionaire. But for now, I got to deal with the current technology. Anyways, so if we can't use this, what are we doing here? Well, we need to minimize the losses at the other end. Because if we eat all the energy up along the way, well, that's just not any good. You're going to lose tons and tons of energy the whole way, and you're not going to be able to run the appliance on the other end. Now, I did some calculations, and to minimize the loss and say we're only going to lose 2% of the energy the whole way, we need 1,000 MCM cable. Now, this is a lug, okay? You can see how big it is. This is for 350 MCM or 350 kc mil cable. This is huge, all right? This is big, all right? Here's that 2 watt I was showing. All right, 350. Whoa, this don't look so big anymore. I don't even have 1,000 MCM cable, okay? It's 1 1/4 inches in diameter across. I got a PEX ring here that's that big or across. The lugs for it, I mean, this would fit in here. The lugs for this kind of cable are like the size of my palm of my hand. They're huge, huge lugs. All right? But not only is it 1,000 MCM cable. No, we need 7 of the things. 7 1,000 MCM cables in parallel running 1,000 feet. And at the end, the voltage would be 11.75 volts. We got less than 2% loss of energy. That's great, right? How much did this cost us? Well, we're running, 14,000 feet of copper 1,000 MCM cable, and the cost comes out to $330,000. Boy, that is one expensive air conditioner. Horribly expensive. Now let's flip that over, right? Let's say we're going to be a little smarter and we're going to pump the voltage up. Let's do times 10. So 120 volts, standard AC power. We're going to go 1,000 feet. And we want less than 2% loss on the other end, right? Well, we do that. It's 8.3 amps Okay, right? 14 gauge work. Well, no, remember? Told you, energy gets eaten as it travels down the wires. We're actually going to need 1 gauge wire. Now that is a heck of a lot smaller than 1000 MCM wire. And guess what? We only need 1. That's a ton better. Still, that much wire over that distance and stuff like that comes to around $3,000 something. A bit more reasonable, you know. Still very expensive air conditioner for a little tiny shack, but we can do that a lot better. Plus, can you imagine running 7 bundles on both sides, going down a huge conduit to get this thing hooked up? It'd be crazy. Now the voltage at the other end would be about 117 or 118 volts. Hey, that works perfectly fine. I mean, lots of houses have that kind of voltage and all their stuff runs. Oh yeah, that appliance would work, no problem. Voltage drop is extremely important when calculating and figuring stuff out. Now, let's go over on heat. Right, you hear about brownouts, transmission lines sagging and stuff like that. Well, a lot of the transmission lines out there, most of the ones you see a lot of places, they're actually a type called ACSR or ACSS. That's aluminum conductor, steel reinforced, or steel supported, okay? It means they have a steel core, and that's what provides a lot of support. Now, those wires are engineered to get hot. And at times when we have immense demand for electricity, those transmission lines, well, they get really hot. And what happens is, they get so hot, the metal expands, sags down, touches the ground, shorts out. That's what they're talking about when you see those in the news reports, okay? The reason is the resistance, that energy getting eaten up as the energy travels down the wire, is converted into heat, all right? We can directly calculate this, okay? There's a little calculator and stuff like that. So when you actually have the voltage drop, when it says, hey, the voltage drop is done by blah, and if you look onto the side where we calculated that out, what you can do is plug that number in. Okay, and you can see the direct amount of heat. We're going to relate this to watts. Sort of like, you know, a 700 watt electric heater, 1000 watt electric heater. This will be directly relatable. Now let's do an example here. Let's directly relate this to some heating, you know, like 750 watt heater, 1000 watt heater, sort of things like that, and give a really good example. Okay, so here's some 10 gauge wire. All right, you know, it's a bit smaller, see? Quite a bit smaller, right? It's a little wire, right? And let's say we want to put 1000 amps down this wire, but we're going to go a foot. Now, when you calculate this out, 1000 amps over 1 foot of this wire, less than 2% of energy loss. Hey, that's great. We can do this. No problemo. Perfect, right? Everything's good. Well, not really. See, the loss is actually, surprisingly, 2 volts. Oh, yeah. So that means, you know, you got 1.6% loss. That's not bad, right? Well, like I said, it goes into heat, right? So this wire, 1 foot long, you take the watts, and so we take the voltage, 2 volts, times the amperage, 1000. This little wire is a 2000 watt heater. Whoa! As you can imagine, this will get glowing red hot, probably melt, and burn everything off and start a horrific fire. This is why you do not run 1000 amps down wire this size. And that's important. The resistance of the wire directly determines how much heat and stuff is released over a given area. And that is very, very important. So when we're engineering these things, I calculate the heat loss because I don't like my conductors getting hot. In fact, I don't like them to rise at all. I over-engineer big time. I like things to work at the maximum worst case condition with very little problems. I don't like conductors heating up. I don't like much things changing. So when you see my stuff built and you go, oh my gosh, Reed, that's like so overbuilt. Yes, it is, for a reason. I like my conductors cool and calm. Cool like cucumbers. So I hope this teaches you some stuff. In the next video, we will go into some much deeper calculations and discuss Ohm's law. And you don't want to break the law. Ohm's is not forgiven at all. Take care, everyone. I hope I was able to teach something and relate this across. And I got to work on getting this stuff a little better and presenting it because it's a little difficult trying to wrap my head around how I want to get this out and explain it. Nothing's easy in the world, is it? Well, this is Reed, out for now.